Hello friends, today we are talking about gravity. So if you take something and you drop it, you release it from rest, and from rest means that it starts with a velocity of 0. It starts not moving, and then you let it go. Does it accelerate? Well, sure it does. Initially it wasn't moving, then it starts to move, so its velocity is changed, and it speeds up, so, gravity accelerates things. When something falls, does it keep changing speed? So if you were to drop a rock from like a foot above your hand, and then you were to drop that same rock from a hot air balloon, you'd probably be a lot less inclined to catch it if it was from a hot air balloon, because it speeds up the longer it travels. So the longer it falls, the faster it gets, okay, until it reaches something called terminal velocity, which we'll get to later. So and the acceleration number for gravity is negative 9.80 meters per second squared. This is the rate at which things accelerate if they are in free fall. And that basically means that if air isn't acting on them, if the air isn't slowing them down or acting as a resistance, so there's no wings or anything like that. So gravity is 9.80 meters per second squared. And the symbol for that is a little g, which we should see sometime. So if you were to drop a 1 kilogram chunk of lead and a 5 kilogram chunk of lead, and that is noted by different sizes, which would hit the ground first, the heavier one or the lighter? Whoops. So which would hit the ground first? Well, they would both hit the ground at the same time if they both accelerate at 9.8 meters per second squared. So get that number in your mind. 9.8 meters per second squared is gravity. Now, do light objects and heavy objects really fall at the same rate? Well, yes and no. So, for example, if I were to take two 1-pound magnets and I were to drop them, they would fall and hit the ground at the same time. Now, let's say they suddenly touched. Are they going to speed up and suddenly start falling twice as fast now that they've got twice the mass? No, just because they touch isn't going to make a difference as to how they accelerate. So heavy and light objects do fall at the same rate. But there is a caveat to that. That's in the absence of air resistance. If I were to drop a rock in a piece of paper, they certainly wouldn't fall at the same rate, unless I crumbled up the piece of paper and made it very, very dense. In which case, if I were to drop that, then they would fall almost at the identical rate. Air resistance tends to muck that up a little bit. There was they did an experiment on one of the lunar missions where they dropped a feather and a hammer on the moon, and the moon doesn't have any air. And what they found was that they did fall at the same rate, just like Galileo and Newton and all the others predicted. So you can Google probably this up here, and they've got this massive vacuum chamber, which means they can suck out all the air, and they drop a bowling ball and a feather, and they find that they do fall at the same rate. So if you're interested, Google that video or Google NASA's vacuum chamber and that sort of thing. So so G, so the symbol for gravity is the lowercase g, equals 9.8 meters per second squared. Should G be positive or negative? Should that 9.8 be positive or negative? Well, it's down, right? So typically we consider right positive and left negative, and up positive and down negative. So traditionally it should be a negative, negative 9.8 meters per second squared. Now, when we're doing stuff just kind of in our heads, we're going to round that number to 10 because it's pretty close. But when you have your calculator handy and you're working on a worksheet, and I give you room to work, space to work a problem, then you want to use 9.8 or negative 9.8 meters per second squared. So so if we drop an object from rest and just put things in a table form. So initially, at time 0, the object is at rest, so we're dropping it from rest. Now gravity is going to change its velocity by negative 9.8 meters per second every second. That's what meters per second squared means, meters per second per second. So, and if we round that, negative 9.8, we could say it's about minus 10 meters per second. So after 2 seconds, gravity is going to change its velocity by another negative 9.8 meters per second squared. So it would be moving at negative 19.6 meters per second, or about minus 20 meters per second. And so that's just the deal. Gravity changes its velocity by about 10 meters per second every second. Okay, so after t seconds, this would be moving at negative 9.8 t, or about negative 10 t. So anyway, so kind of the main point so far is gravity is negative 9.8 meters per second squared, and gravity changes the velocity of an object by about 10 meters per second every second. So if I were to drop a penny from the Empire State Building, and I said how far or how fast is it moving 4 seconds after you let it go, it would be moving about 40 meters per second down, or negative 40 meters per second. And after 9 seconds, it'd be moving about negative 90 meters per second, ignoring wind resistance. If we were to graph a velocity versus time graph for an object in free fall, a dropped object or a thrown object, in this case just dropped. So after 1 second, it would be moving at negative 10. After another second, it would be moving at negative 20. After another second, it would be moving at negative 30. And we just get this straight line. And that's what a velocity versus time graph would look like for something that was dropped. And if we were to interpret this, we would say it's moving backwards or down, okay, because we're in the negative region. Velocity versus time graphs, remember, positive region, negative region. We're moving backwards or down because it's in the negative region, and it's speeding up because it's getting further away from the axis, or the zero line. Okay. Okay. Now, if I were to ask you what's the initial acceleration when it was at rest, not what the initial velocity is, not the initial velocity, but the initial acceleration. Okay. Well, as soon as something is dropped, the acceleration is negative 9.8 meters per second squared, or about 10. So that the initial velocity is 0, but the acceleration is still g. It's still negative 9.8 meters per second squared. Okay. So here we take a stone and we drop it. So initially it's at rest, it's at 0 meters per second. After 1 second, it's moving at about negative 10 meters per second. After 2 seconds, its velocity is about negative 20 meters per second. After 3 seconds, its velocity is negative 30 meters per second. And these would be V2s. This would be our V1, and this would be our V2, or our next V2. And then after 4 seconds, be moving at about negative 40 meters per second. So, are these average velocities or instantaneous velocities? Well, this is what the speedometer on this rock would read. Right after 1 second, it would read negative 10 meters per second. Or after 2 seconds of falling, that speedometer would read negative 20 meters per second. So that is the instantaneous velocity. That's not the average velocity. If we want to start talking distances, we have to know the average velocity, and that's what we'll look at in the next slide here. So, what is the average velocity during the first second of free fall? So we're just going to look at between 0 seconds and 1 second. So, well, V1, the equation we're using is average velocity equals V1 plus V2 divided by 2. So add them up and divide by 2 is basically what we're doing. So add them up 0 and negative 10 and divide by 2, we get minus 5. So the average velocity is minus 5. Okay. How far did it travel in 1 second if it was going at an average of minus 5 meters per second for 1 second? Well, it's going to go 5 meters. Okay. How far will it fall in 2 seconds? Okay. Well, what's the average velocity? Well, add them up and divide by 2. So the initial velocity is 0, V1. The V2 is 20 meters per second. So add them up and divide by 2. So that's 10 meters per second. So our average velocity is 10 meters per second. And we do that for 2 seconds. How far do we go? Well, that's speed times time, or velocity times time, gives me displacement or distance. Okay. So 2 times 10 gives me 20. Okay, in 3 seconds. Okay, let's look at our initial and our final velocities. So 0 and 30. So add them up and divide by 2 to get my average. That's 15. Okay. and then 15 times 3, our time, gives me 45. So it falls 45 meters. And last one on this one, and you're going to be doing something similar to this on the worksheet. So hopefully you can kind of make some sense out of this. So what's the average velocity v bar after 4 seconds? Well, 0 and 40, add them up and divide by 2 gives me 20 meters per second. And then multiply that by your time to get your distance or displacement. And that's going to be 4 times 20 is 80. So that's how we get those. Now if we look at how far it falls each second, so in the first second, it just went 5 meters. And then between the first and the second seconds, it traveled 15 meters because it went from -5 to -20. Okay, there's kind of a lot of numbers going on here, so stay with me. In the next second, between the second and third second, it went from 20 to 45, so it went 25 meters. And then the last second it went 35 meters. So notice that each second it's falling a greater distance. Why would that rock be falling a greater distance each second? Well, that's because it's getting faster. Okay, it's speeding up. It's getting faster. That's what happens when things fall. They get faster. Okay. So this is a motion diagram for a ball that's dropped from rest. You can see that the spacing gets increases exponentially. At least I think I made it increase exponentially. Now this is what a displacement versus time graph would look like for an object dropped from rest. So we would say, well, it's moving backwards or down, okay, because the line is going towards the negative region. It's sloped down. It's got a negative slopish. And it's getting steeper, which means it's speeding up. So it starts off very flat and then ends up kind of steeper. So it's going to be getting faster. So it's moving backwards, or in this case down, and speeding up. And that's what happens when things fall. Okay. So how much does the velocity of an object change by each second of free fall? Well, it changes by negative 9.8 meters per second each second. Okay. Meters per second squared. How much does the displacement or the distance change each second? Well, that changes because it's speeding up or slowing down. If it's on its way up, it can be slowing down, which we're not talking about that today. Okay, so let's say we drop a rock after 9.5 seconds. Okay, what is its velocity? What is the average velocity? And what is its displacement, aka how far has it fallen? So we're going to be going back to our 3 equations that we talked about before. So v bar equals delta x over t, also known as equation 1. We've got equation 2, v bar equals v1 plus v2 over 2. And we've been using these equations today. So when we've been adding them up and dividing by 2, we've been using this equation. When we multiplied the average velocity by the time to get the displacement, we've been using this equation. We haven't used this equation yet, but we will. Okay, so the first question is, after 9.5 seconds, what is its velocity? So we know our initial velocity is 0. Our time is 9.5 seconds. The acceleration is negative 9.8 meters per second squared. What is its velocity after that at that time? So we're looking for v2. If we're looking for the velocity at a later time, that's going to be v2. So we use equation 3. v2 equals v1, which is 0, plus negative 9.8 times 9.5, and we get our v2 is equal to negative 93.1 meters per second. Okay, for b, we want to figure out the average velocity. So our initial velocity was 0, and our v2 is negative 93.1. So add them up and divide by 2, and you get 46.6, negative 46.6. And then last, how far did it go? If you're looking for how far did it go, okay, you're either going to be using the speed equals distance over time equation or the v bar equals delta x over t equation, which in all of this stuff you're going to be using this equation, v bar equals delta x over t. Now, I played a trick on you. Instead of putting delta x on top, I put delta y for the displacement. Why would I put delta y instead of delta x? give you a hint, it means mostly the same thing. It means how far the object traveled, but because it's moving up and down in the y-axis, I put delta y there. So we use the equation v bar equals delta y over t. We just figured out v bar, and then we plug in our time, multiply through, and you get negative 44.2 or negative 442 meters. So that's the first example. Okay. Another example, you're standing on a bridge and you drop a rock, you hear it hit 6.8 seconds, and you want to figure out how high you are above the ground. So here's your rock. Okay. You drop it from rest, so you know your V1 is equal to 0. You're looking for the height of this cliff, okay, and you know that after 6.8 seconds, so your time, that's when it hits, that's when it reaches the bottom. And because we're dropping things and whatnot, our acceleration is negative 9.8 meters per second squared. So first off, we're looking for how we want to figure out delta y, or delta x, delta y technically. So we need to know, in order to know that, we need to know v bar and t. Well, we know t, okay, but we don't know v bar. Okay, well, that's fine. I've got an equation to find v bar. In order to find v bar, I need to know v1. Well, I know that. That's 0. And then I need to know v2. I don't know V2. Oh, look at that. I've got an equation to find V2. So the V2 equals V1. I know that. Plus acceleration. I know that. Plus time. I know that. So what we're going to do is we're going to start and we're going to work our way backwards. And you'll find yourself doing this a lot of times, working your way backwards from 3, 2, 1. So we're going to find V2, plug that into the second equation, and then find v bar, and then plug that into the first equation. So that's exactly what we do. So use equation 3, v2 equals v1 plus at, and you get v2 equals negative 66.6. Then we use equation 2, 0 plus a negative 66.6 divided by 2 gives me negative 33.3 meters per second. Okay. And now that I know v bar, now I can use equation 1. You got to know v bar to use equation 1 to find displacement. And anytime you find displacement, you're going to be using that equation. Okay, the speed equals distance over time equation is pretty much identical. So you can kind of use them interchangeably because they both say how fast equals how far divided by how much time. Okay, so so then we plug a v bar equals delta y over t, and multiply through by 6.8, and you get negative 227 meters. Okay, and that's how you would have solved that one. So that one was a 3-step problem. So we're getting into some real physics here. The challenge level is definitely is up there. So make sure that if you don't know what's going on, that you're coming by my office hours and getting some help with this, because you want to stay caught up. It will definitely not be fun if you get lost. Okay, so let's next we're going to look at throwing an object downward. So let's see. Velocity, if I throw it downward, is going to be negative, and g is still going to be negative. It's going to be down. So the velocity is going to be the same. So it's going to, the sign on the acceleration and velocity are the same. And what do we know? If the sign of the velocity and acceleration are the same, anybody know this? It's going to speed up. Okay. So let's take a rock and let's throw it down at 15 meters per second. And after 9.5 seconds, we want to figure out its velocity. What's the average velocity since it was thrown at 9.5 seconds, and what is its displacement? So we're going to be working our way backwards, 3, 2, 1 again with this one. Okay. So what's different about this problem is that we've got a V1. My V1 is not 0. My V1 is a negative 15 meters per second. My time is 9.5 seconds, and my acceleration, and all these, rock is dropped, cannonball is shot upwards, rocket is fired upward. Okay, all these things that are falling, the acceleration is always going to be negative 9.8 meters per second squared. So what is the velocity after that time? So we're going to use, we've got V1, A, and T, and we want to figure out V2. We want to figure out V2 when it's right here after 9.5 seconds. So we use our equation to find V2. So V2 equals V1 plus AT. So notice that our V1 is not 0 here. We plug in our A and our T, and we get negative 108 meters per second. The next question is, what's the average velocity? So again, I'm not averaging this 108 with 0 here, because my V1 is not 0. My V1 is negative 15. I'm averaging that with negative 108, and I get negative 61.6 meters per second. And then the last question is, how far has it fallen? So if you're looking for a displacement, delta y, okay, which is equation 1. We use the average velocity, and we use the time and multiply through, and you get negative 585 meters. Okay, so that is it for these notes. Work on 2.5.